Hey there, welcome back. Here we go into video 2 of the basics of parametric equations. In this one, we're going to talk about how to eliminate the parameter and really talk about what that is. It's not so bad, and it's something that a lot of teachers and professors do ask you to do, so let's not hesitate and jump into it. So we're asked to eliminate the parameter in the given set of parametric equations. We've got the same set that we used in the previous video where we graphed it out. So what does it mean to eliminate the parameter? Well, remember that the parameter is, in this case, t. It's the independent variable that we plug in for. It could be theta, it could be r, it could be s, it could be any number of variables, usually not x or y, that we plug in for. So we're going to eliminate it. Now to do that, what we do is we pick the equation that is easier to solve for t in terms of another variable. So in this equation, to solve for t would require some completing the square or quadratic formula. No thank you. In this one, it wouldn't require much. Just subtracting 1. I'll show you what I mean. I tend to like to get rid of the x of t and just write it as x equals t squared minus 2t and y equals t plus 1. It makes the solving easier. So I'm going to solve for t in terms of y, just because it's easier. We could have solved for x in terms of, or t in terms of x. It's easier to solve for t in terms of y. So I subtract 1 from both sides, and there you have it. We have what's going to now act as our translation, if you will, from parametric land into, well, regular old rectangular form. Not that this isn't rectangular, but regular in terms of x. So I'm going to take y minus 1 equals t and plug it in here. Or in terms of y, actually, in this case. So I take y minus 1 and I go like that. Maybe it doesn't make that sound. The reason why I do that is because we are now told that t is y minus 1. So I plug that in, I get x equals y minus 1 is getting replaced for each t value, squared, minus 2 times y minus 1. And you'll notice this is going to be some sort of a quadratic, but it's in terms of y. So, I mean, we could simplify this down a little bit more, and people will do that, and maybe I'll do that on the next page, but for now, you've eliminated the parameter. Just how far you need to simplify is up to the expectations of your teacher or professor. This kind of thing, I've never seen it asked for on the BC exam, by the way, but it's still a skill that I'd expect of my students, for sure. So then this says, what is the point in eliminating the parameter? The purpose of doing that is honestly to just kind of understand the shape of what the graph would look like or be a little bit more comfortable with the parametric equations because we've spent years on graphs like this and understanding functions like that, x in terms of y or y in terms of x, but we haven't spent much time with parametric equations. So it's just to be able to look at it and say, oh, okay, it's y squared, and then kind of look out from there. So how much you want to simplify this is kind of up to you. What I'm going to do is I'm going to take this work over here and hopefully nope, it's not letting me copy it. Oh, well. So I'm going to take that value and I'm going to bring it over to the next page. Here we go. So this is what ends up simplifying from that. So we had y minus 1 squared, and I'll just kind of show that out. X equals y minus 1 squared minus, and it was 2 times y minus 1. And so what you can do from here is you can simplify this out and expand it. This would be y squared minus 2y, foiling this out, plus 1 minus 2y, distributing, plus 2. And when you combine everything together, you'll get plus 3 minus 4y, and then y squared. This, I then took the liberty of completing the square, which you don't have to know how to do, but I wanted to show you that what's happening here is we have a parabola. That's what the graph looks like in terms of y. So because you have a positive value out here, we're facing to the right. Our vertex is the point, well, that's going to be -1, +2, and sure enough, that's where we are, -1, +2, and again, it's facing to the right, and it's parabolic. That's it. So that's really one of the main points of eliminating the parameter is just writing a parametric equation in terms of something that we're familiar with. That's it. All right, so there's more than one way to eliminate a parameter, however, and this is one that I love. So what happens when you have trig functions? How do we eliminate those kinds of parameter situations? Well, again, I like to convert everything to not x of t, but just write it as x equals cosine of t, y equals sine of t. Now, in this case, solving for t in either one of those is a pain. It would be awful because solving for t here would involve doing sine inverse of y equals t. And then you'd plug this in here, which is it's all doable. But there's a better way. Let me show you. We can square each of these equations. It still yields truth. X squared is equal to cosine squared t, because x was equal to cosine t. Same thing here, y squared is equal to sine squared t, because y is equal to sine t. And what we can do is we can add two truths together. X squared plus y squared, adding these two equations together, would therefore be equal to cosine squared plus sine squared. Oh, do you see where I'm going here? If you don't, you're about to. Now there's an identity in trigonometry that says cosine squared plus sine squared is equal to 1. We'll take out the middle dudes, and we get x squared plus y squared is equal to 1. And why is that important? Where'd the parameter go? Poof, it's gone, right? So you're left with an equation with no t-value whatsoever, and a simple equation for a circle with center at 0, 0, and radius of 1, which is exactly what this set of parametric equations would look like. So I want to talk about why that actually makes sense, that this set of equations would give you a parametric equation like that, because it makes some sense. So if we plug in, and I'm going to plug in some t-values here just for giggles, just for a moment, we're not going to do every single one of them. We have x equals cosine of t, and we have y equals sine of t. Now if you think back, this is exactly what the unit circle was all about, right? X was the cosine value, y is the sine value. So we're going to pick nice values in the unit circle. 0, pi over, 4, pi over 2, 3 pi over 4, and we'll go to pi. And then I'll just kind of go and I'll skip to 3 pi over 2, and then 2 pi. So if we plug these values in, cosine of 0 is 1, sine of 0 is 0. So that's this point right here. Cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is also root 2 over 2. So what starts to happen is, that's about the halfway point where cosine is decreasing the entire time. So you're kind of bending inwards. You're going to the left in the x value. At the same time, the y value is going up. So if we go left and up, oh, you're going to end up, that's pretty cool, right? So you start out over here to the right, you go left and up, you're bending in. That gives you that first really nice quarter circle. So cosine of pi over 2 is 0, 1. And then we get root 2 over 2, but a negative. And here we get a, well, positive root 2 over 2. So now we're bending back around. Here's what's happening is we're going further left and closer to 0. That completes the second part of this circle. And at pi, we're at negative 1 and 0. So that's where we bend back around. Isn't that cool? I think it's pretty neat. And then we repeat. 3 pi over 2, we're going to get 0, negative 1. So this entire time, we're now going downwards, and we're starting to come back towards the right, which completes this part of the circle here. That's neat. And then to 2 pi, we're back at 1, 0. We bend back around. So we're moving up the entire time, and then down. And the whole time, we're moving left. So if I go up, and then down and left, here we are. And then the entire time here, I'm moving down until I get to 3 pi over 2 and to the right. And then I'm moving up and to the right. So looking at this as two separate motions rather than just one fluid circular motion, we can see that we get that one fluid circular motion. It's the unit circle. And a really neat way, by the way, to complete eliminating the parameter. So anytime you have trigonometric functions, look for that Pythagorean identity is what it's called, and squaring both equations, adding them together, and rocking and rolling from there. So that's pretty neat. Okay, we've got one more idea here on the docket, and that would be eliminating the parameter. But the other way. We're actually going to create the parameter. Oh my goodness. I call it parameterizing. I've never heard that word actually in a dictionary. It's probably not a real word. But how do we parameterize something, make it parametric if it's not? Well, it's up to you to just kind of let one of these values be something. So here's the normal function that I showed you. Like I'm letting that just be x equals y to the fourth minus 3y squared. That is what the function looks like. Pretty funky. And it's not a function, I should say. That's what that graph looks like, that relation. So I'm going to let y equal t. You could let y equal t squared. That would certainly affect the shape sometimes. I'm going to let y equal to t. By doing that, x is therefore equal to t to the fourth minus 3t squared. So what you end up with is the same x motion. You're going to be moving left, right, and the whole time we're going to be moving bottom to top. So that would be the direction of motion. Now we give it motion all of a sudden. So left, right, and moving up and down would get us to go along that curve. That's pretty neat. So that's it. Now in some tests, some teachers will say, let y equal to, and they'll dictate t squared, t to the fourth, root t, whatever it is. I'm just saying the easiest way is just let the variable that's independent, the variable that's got all the stuff being done to it, be equal to t. All right, that's it. That was it for eliminating the parameter as well as parameterizing. Very cool. I'll see you in the exercises. Peace.